our last example, we're going to work a 3 by 3. I promise you with these repeated eigenvalues, I won't give you anything bigger than a 3 by 3. So this one's 1, 2, 0, 1, 1, 1. 1, 1 minus 1, actually. This is from the book Problem 4. 1 minus 1, 1 in section 7.8. Okay. And so you want to find the general solution. So remember, on the test, these will all be mixed up. You won't know, oh, this is in the repeated eigenvalue section. Okay, you just have to work it out and see what happens. So as usual, step 1 is to find the determinant of a minus lambda I and set that equal to 0. So that's the determinant of 1 minus lambda 1, 1, 2, 1 minus lambda minus 1, 0 minus 1, 1 minus lambda. And let me just make sure I copied it down, because you can get into some real messes if you copy the problem incorrectly, because eigenvalues can become horrendous. Okay. And now you want to set that determinant equal to 0. So let's use the row that has the 0 at the bottom. I'm going to expand around that. So this is plus minus plus. So it's 0 is plus, then it'll be minus this one. So it'll be plus 1 times the determinant of the matrix you get when you delete the row in the column containing minus 1. So that'll be 1 minus lambda 2, 1 minus 1. And then that was a minus, so this is a plus. 1 minus lambda times delete the row in the column containing 1 minus lambda. You get 1 minus lambda 1, 2, 1 minus lambda. Okay, so this says 0 is minus 1 plus lambda minus 2, right? Minus 1 plus lambda minus 2 plus 1 minus lambda times 1 minus lambda squared minus 2. Okay, so this becomes 0 is lambda minus 3. And then here you'll get a 1 minus lambda cubed. And then you get a minus 2 times 1 minus lambda. Okay. All right, so we just have to expand everything out and see what we get. So we have lambda minus 3. When you cube this thing, you get the cube of the first. Sorry, you'll get a square of this one times that one. So it'll be and the coefficient by the binomial expansion theorem, which I hope you remember, plus 3 lambda squared minus lambda cubed. And then you'll get a minus 2 and a plus 2 lambda. Okay, so let's see, that gives me a minus 3 lambda plus 2 lambda and plus lambda. That goes away. And then we have a minus 3 and a plus 1 is a minus 2, and this minus 2 gives you a minus 4. I'm going to go, okay, so that'll give me a minus 4, and then I have a plus 3 lambda squared, and then a minus lambda cubed. So that's the same thing as saying 0 is lambda cubed minus 3 lambda squared plus 4. And I don't know the roots of that offhand. Doesn't factor very nice. So you look at the possible roots. That's the possible factors of 4 divided by the possible factors of the top order coefficient, which is just 1. So the possible roots of 4 plus or minus 1, plus or minus 2, plus or minus 4. Okay. So I don't know. I'm just picking randomly. So we'll copy down the coefficients. Now remember, when you do this to do synthetic division, you have to include a term for the lambda power, which doesn't appear there. It means its coefficient is 0, and then 4 is the constant term. And I don't know, let's try, let's see if I can do this quickly in my head. 2 is minus 1. Let me try minus 2. So this will be minus 2, that's minus 5. This will be plus 10 and 0. Okay, that's not going to work. So let's try minus 2. Okay. Okay, so that is 2. That gives me a minus 1. That gives me a minus 2. When I add, I get minus 2. Here I get minus 4, and that's 0. So that works. So this thing factors to 0. You get a lambda minus 2. And then this is lambda squared minus lambda minus 2. And now that one's easy to factor. That factors to lambda minus 2. So that becomes a lambda minus 2 squared and a lambda plus 1. Okay. So your eigenvalues are lambda is 1, or minus 1 rather, and plus 2. It's a simple eigenvalue. It's multiplicity 1, and this one has multiplicity 2. So we're going to need 2 linearly independent eigenvectors for lambda equals 2. Okay. So now we have to find, but we need all 3 eigenvectors. So for lambda equals minus 1, we need an eigenvector that satisfies a minus a minus 1, so that's plus I, times x minus 1 equals 0. So that is, that gives me, so here's mine. You can always look back. A minus lambda I is written in there where you're taking the determinant of it. So you can look back there to copy down your matrix. So here lambda is minus 1. So that gives me a 0, 1, 1. And then that gives me a 2, 0, minus 1, and a 0, minus 1, 0. Times, let's call these components x, y, z. And that equals 0, 0, 0. Okay, and now we got to work that out. So I got to put the 2 is going to have to come and be the top row. And let me go ahead and multiply by a half while I'm doing that. So I'm switching these two, and I'm multiplying the top one by a half. So that becomes a half row 1. It'll be 1, 0, minus 1 half, comma 0. Because I'm taking this, writing out the system of equations, which we've done a lot of times now. And then you make the augmented matrix to work with that. And so I can just skip right in, because we have so much work to do. We just go ahead and switch these rows on the first go round. And the second row will be this. And then the third row is 0, minus 1, 0, 0. Okay, now the second column is almost clear, except I got to get rid of this. So I'll add row 2 and row 3. And that'll give me 0, 0, 0, 0. Okay, and now and then this one's in the best shape it can be, and this one's in the best shape it can be. Because you need a row of all zeros, or you did something wrong in your calculations. You're always going to need that for eigenvectors. And now this row tells me that x minus z over 2 equals 0. And this row says y plus z equals 0. So x is z over 2, and y is minus z. So if we pick z to be 2, because I'd like to avoid a fraction, if z is 2, then y is minus 2, and x is 1. So there's an eigenvector corresponding to minus 1. Okay, and now we look for an eigenvector corresponding to 2. Well, we actually look for 2 of them. That's the hope. So this will be a minus 2 times I times x2 equals 0. So a minus 2 times the identity will be minus 1, 1, 1, 2 minus 1, minus 1, 0 minus 1, minus 1. Again, let's call it x, y, z. And that has to be equal to 0, 0, 0. So you multiply that out, 3 equations and 3 unknowns. You write it into an augmented matrix so you can row reduce to find x, y, z. Let me go ahead and multiply by minus 1 as I write this one down. So this will be 1, minus 1, minus 1, 0. And then to get rid of the 2, I'll do minus 2 times row 1 plus row 2. So that'll give me a 0. That gives me a plus 2, and a minus 1 is 1. That gives me a plus 2, and a minus 1 is 1. 0 and 0 is 0. Okay, and then this row I just write down. Okay, and now I add row 2 and row 3, and I get a column of all zeros, which I mean a row of all zeros, which I expect. And now I use this one to clear out that one. So I'll say row 2 plus row 1, and then I get 1, 0, 0, 0. Okay. Okay. So what does that tell me? The first row says x1 is 0. The second row says y plus z equals 0. So y is equal to minus z. So x is 0 and y is equal to minus z. So here's an eigenvalue for at lambda equal 2. One eigenvalue would be, let's pick z equal 1, then y is minus 1, and x is 0. But we only got one eigenvalue. I mean, only one eigenvector out of this. We need two linearly independent eigenvectors. Okay, so when that happens, you have to start to play the game that we saw on the last one. So that means we look for an eigenvector. Oh, well, let me finish writing this down. So our first solution, so x1 of t is going to be, well, okay, sorry. So we have one solution we get from taking e to the minus t times this eigenvector. We get a second solution by taking e to the 2t times this one. And now we need a third solution. Okay, so here's how we look for the third solution. x3 of t, we're going to look for a solution of the form, we're going to look for a solution of the form t e to the 2t times the eigenvector we found before. Okay, that's what I called C in the other notes. And then I need plus e to the 2t times eta, where eta satisfies a plus 2 times the identity, sorry, a minus 2 times the identity times eta equals C, the eigenvector from before. Okay. So let's say eta has components, I don't know, what shall we call it? What we haven't used before. How about A, B, and C? Okay, we got to find A, B, and C. Okay, so A minus 2 times the identity. A minus 2 times the identity in this problem will be, so you look back and you notice I just can't fit it all on here. So here is A minus 2 times the identity. Times eta, which we said the unknown, the components of eta, we're calling them A, B, and C. That's what we have to find. Has to be equal to the first eigenvector that we found for lambda equals 2. Again, I remind you, this is just a matrix equation. Sorry, eta equals C. So that's exactly what I just wrote down. So C is the eigenvector from before. Eta is the one we have to find. This is A minus 2i. So this gives me 3 equations and 3 unknowns. You could write it out. For example, the first equation says minus A plus B plus C equals 0. And then the second equation and the third equation. And so this is what I've been doing and just skipping right in that part because we're so familiar with this. And now when you write the system of equations to go to solve it, you make a big augmented matrix and row reduce. So when I go to write down the matrix, look, I have a -1 here. I got plenty enough work to do, so let me just go ahead and multiply row 1 by -1 as I copy it. Okay. And now this row is fine as it is. And now for the second row, I want to get rid of a 2, so that'll be -2 times row 1 plus row 2. It'll be -2 and +2 is 0, +2 and 1 is 3. I'm sorry, that was wrong. That's +2 minus 1 is 1. And +2 minus 1 is 1 and 0. And I'm sorry, this should have been a C here. And this should have been a minus A. So used to doing the homogeneous ones because we did so many of those. Okay. But this is, let me try that again. Here's my inhomogeneous terms. It's 0 here. Okay. So when I do -1 times that, it's still 0. This would be I did -2 times row 1 and add it to row 2. This would be -1. And this one I'm just copying down. Okay. Again, maybe it would help in this case because it's a little bit different to write out the equations. Okay, so there's our equations. Here's the augmented matrix for that, and I've already started my matrix to row reduce. Okay, and so now once I get this, I can clear out this bottom row by simply adding row 2 and row 3. Then I'll get 0, 0, 0, C minus 1. Okay. Okay. Now we got to be careful with all of these rows. Now with this one, that's just by adding row 2 and row 3. I got that. And now to get rid of this -1, I better add row 2 and row 1. So that'll give me 1, 0, 0, -1. And the second row stays like it was. Okay. I'm sorry, this is not a C. This is a 1. Copied that wrong. This is it. Here's the right-hand sides. This should be the right-hand sides. So when I add row 2 and row 3, I should get 0. Sorry. Tired. Okay. So that's a row of all zeros. That's what we expected. All right, so we're in business. So now we can translate back. These are the coefficients of A, B, C, and this is what comes after the equal sign. So the first row says A is equal to -1. The second row says B plus C is -1. And the third row says nothing. So this says that B is equal to -1 minus C. Okay, so it says our eta has to be a vector of the form -1. Now pick C to be anything you want. So let me pick C to be 1. And then B will be, if C is 1, then B is -2. Okay, so that's our eta. Okay, so then our third solution then is TE to the 2T times 0 minus 1, 1, plus E to the 2T times eta. Okay. Okay. And I actually, it probably would have been better to go ahead and leave the C as arbitrary. So, yeah, let me go back and do it in the most general way. So A is -1, C is this, and B is -1 minus C. Okay, so then we have minus 1 minus c, and we have c. So you can write this as t e to the 2t, 0 minus 1, 1, plus e to the 2t times, you have the vector minus 1, 0, plus c times the vector 0, minus 1, 1. Okay. And now you notice that c times minus 1, 1 will be absorbed into this guy when you put an arbitrary constant into it. So if I multiplied by, um, if this were multiplied by C3 and this had a C4, then this would be C4 and then this would be CC4. So this one combines with this, with the one, not with this one, but okay, I'm messing this up a bit. When we put let's leave C3 in here, these can have arbitrary constants. So let's leave it like that. That means this is a C4 and this is a C4 with an e to the 2t times it. Can't drop the e to the 2t. Okay, so I just wrote this vector out as minus 1, 0, plus 0 minus cc, and then factored out the c. Okay, so now when I go to write the general solution, that's x of t, is C1 times the first solution we found, plus C2 times the second solution we found, plus C3 times this third solution we found. Okay, so the first solution we found was, where is it? Okay, so we found for lambda equals minus 1, here's our eigenvector. 1 minus 2, 2. So this is C1 e to the minus t, 1 minus 2, 2. Okay. And then we have plus C2. The second solution we found was for lambda 2. Lambda equals 2, so that's e to the 2t. And the first eigenvector we found with that was 0 minus 1, 0. And then the third solution we found, so we'll take C3 times that, was t e to the 2t times 0 minus 1, 0, plus e to the 2t times eta. Okay, and we just found what eta was. Eta, let me put it down here because it's just not going to fit. So you get a C3 times eta. And what is eta? Eta is minus 1, 0, plus another multiple of e to the 2t times 0 minus 1, 1. But that's the same thing as this, so it only changes the C2. So this piece gets absorbed in that term. This piece gets absorbed in this term just by changing the constant in front. Okay. So that's the answer, and it looks very long, but that's just the nature of these problems. So I hope this lecture helped to clarify the description in the book for homogeneous systems with constant coefficients when you have repeated eigenvalues. The next video will give another example because I think you need to see a little more practice on these type of problems. Okay, so see you in the next video. Bye.